Friends, Professor T. N. Oza here. Now we are going to start a new series of videos based on thermodynamics. Because the topic of thermodynamics is very lengthy, we will try to make it in small pieces. So nearly 10 videos will be presented on this topic. Let us begin with the introduction. Thermodynamics deals with the mathematical relationship between mechanical work and various forms of energy changes such as heat, internal energy, enthalpy, entropy, gives free energy, work function, etc. The fact that thermodynamics is based on mathematical evidences, it is regarded as an exact science, as opposed to quantum mechanics, which is based on approximation. Further, thermodynamics supplements chemical kinetics, which deals with the rates of reactions and physical processes, but does not state about the feasibility or non-feasibility of the process. Thermodynamics does that, but it fails to predict rate. So both are supplementary to each other. Importance of thermodynamics. The subject of thermodynamics is of tremendous academic as well as industrial importance. Most of the industrial processes make use of the principles of thermodynamics. Most of the generalizations of physical chemistry, such as activation energy for chemical reactions, want of law of dilute solutions, Raoult's law of vapor pressure lowering, laws of osmotic pressure, and other colligative properties are derived from thermodynamics. Limitations of thermodynamics. Thermodynamics is not free from limitations. It primarily deals with macroscopic systems and reversible processes, but does not deal with the microscopic systems such as atoms and molecules. However, newer developments known as statistical thermodynamics and reversible thermodynamics have opened up new vistas. Terminology. We will be dealing with the following terms: system, boundary, surroundings, state of the system, state variables, extensive properties, intensive properties, exact differentials, inexact differentials, and a few other terms. Any specified portion of the universe which is being studied is called thermodynamic system. It is separated from the rest of the universe, called the surroundings, by a real or an imaginary boundary. The boundary may be rigid, that is constant volume system, dV equal to 0, or flexible, that is volume V can be changed. It may be thermally conducting, heat change dq need not be 0, or insulator, providing adiabatic conditions, that is dq equal to 0. It may be semi-permeable or impermeable. It may be living or non-living. So almost everything can be studied by thermodynamics. And I must tell you, the subject of thermodynamics is no longer limited to chemistry only or physics only. It is widespread. Its principles are being used in social sciences, medical sciences, engineering, everywhere. Types of system. Three types of system we will study. A system may be isolated so that exchange of matter or exchange of heat between the system and the surroundings is not allowed. That is dm equal to 0 or dq equal to 0. Next system is closed system, for which exchange of matter is not allowed, but exchange of energy is allowed. And third may be isolated system. Neither exchange of matter is allowed nor exchange of energy. There exists no ideal isolated system. A thermos flask may be considered as an improvised isolated system. Secondly, a open beaker containing some solution is an example of open system. If the beaker is closed, so that matter cannot get in or get out, it is a closed system, provided its walls are thermally conducting. Further, a system may be macroscopic or microscopic. It may be homogeneous, this is a single phase system, or heterogeneous, more than one phase. A supersaturated solution of aqueous solution of sodium chloride is an example of heterogeneous system. All living beings constitute heterogeneous system. Thermodynamics deals with properties of microscopic system, not microscopic ones. However, recently it has been possible to make deductions about microscopic systems based on microscopic properties. The state of a system. When macroscopic properties of a system, that is thermodynamic variables such as temperature, pressure, volume, amount of matter, etc., can be exactly stated. The system is said to be in a certain physical or thermodynamic state. The state variables T, P, V, E, H, S, G, etc. are path independent. That is, when a system changes from, say, state 1 to another state 2, the change in any of these variables will be exact. That is, the final value of the variable minus initial value. On the other hand, heat and work, they are path-dependent functions. Thus, if we integrate dE, we will get exact value. dE integration gives E2 minus E1, exact value. But integration of dQ, heat, does not give Q2 minus Q1, it gives Q simply. Similarly, integration of dW, that is work differential, gives W inexact value, not W2 minus W1. So we have two types of variables, exact variables and inexact variables. A little later we will discuss more about these things. But at the moment we should remember path functions are exact variables, exact differentials. Path dependent functions are inexact variables, inexact differentials. Work and heat are path dependent variables. Energies of all types, volume, temperature, pressure, etc., they are path independent variables. Extensive and intensive properties of a system. As the name indicates, intensive properties are those which depend on the mass of the system, whereas intensive properties are innate, inherent. They depend on the property of the system. When an extensive property is divided by the number of moles of the substance, it becomes intensive property. The laws of thermodynamics. Actually, thermodynamics is based on 4 statements or axioms. These are called as first law, second law, third law, and zeroth law. The first law is about the conservation of energy of an isolated system. Energy and mass equivalence is also included. The second law states ever increasing entropy of the universe. And third law states at absolute zero, the entropy of a perfect crystal approaches zero value. The zeroth law was studied later. It is necessary to define temperature scale, and because it was formulated later, so it was given the name zeroth law. The basic principal equation of thermodynamics as first law is del E equal to Q plus W, where del E is final E minus initial E, it is E2 minus E1. Q is heat exchange between the system and the surroundings. W is the work done either by the system on the surroundings or by surroundings on the system. As per convention, work is always considered negative, and in thermodynamics of gaseous system, W equals negative P dV integral. The various mathematical forms of first law of thermodynamics are as follows. E equal to Q plus W. It is symbolic. That is definition of E. dE equal to dQ plus dW. Differential equation form showing infinitesimally small change in E, Q and W. Del E equal to Q plus W. Integrated form. Del E equal to QV when volume of the gaseous system is constant. So that PV work is zero. Next form is del E plus P del V equal to del H equal to QP. When pressure is constant, volume changes. It may be remembered that when heat is added to the system, it is given positive value. When heat is taken out from the system to the surroundings, it is given negative value. Work done by the system on the surroundings is given negative value because it is done at the expense of internal energy. Work done by the surroundings on the system is given positive value. For an adiabatic process, Q is 0, therefore delta E equal to W. For a constant volume process, W is 0, therefore delta E is Q. For gaseous system, work W equal to PV work, that is expansion or compression. It equals integral minus P dV. In addition, the first law can be expressed using heat capacity CV and CP, these to be discussed later. Heat capacity of gases. Preliminary, the quantity of heat Q that is needed to raise the temperature of a thermodynamic system by 1 degree Celsius. That is to say, from T to T plus 1 is defined as the heat capacity. If the mass of the system is more, heat capacity is more. So it is extensive property, symbolized by capital C. When the mass of the system is 1 gram, it is given the name is specific heat capacity. It becomes intensive property. And when the mass is 1 mole, it is called molar heat capacity, again intensive property. Two types of heat capacities are used for gases. Heat capacity at constant volume, that is changing temperature and changing pressure. No problem, but constant volume. Its symbol is CV, capital C and subscript V. Another is heat capacity at constant pressure, that is changing temperature and changing volume, constant pressure. The symbol is Cp. Because both type of specific heats, Cv and Cp, they are not truly constants. They vary with temperature, slightly vary with temperature. Within lower span of temperature, these are considered constant. But the tradition is to define them in the differential form. Cv molar equal to del E upon del T at constant V, or Qv upon T2 minus T1 at constant V. Cp molar equal to del H upon del T at constant P, or Qp upon T2 minus T1 at constant P. If a thermodynamic system has mass m gram and it absorbs heat Q so that its temperature is raised from T1 to T2. Then its heat capacity C, joules or calorie per degree Celsius or per Kelvin, is equal to Q by T2 minus T1. And the specific heat capacity is given by C by M equal to Q by M and delta T. The molar heat capacity is given by C by M over Na. Na is a better number because heat capacity is not truly constant, but it varies with temperature. It is defined by differential equation C equal to del Q by del T. From the first law of thermodynamics, for a constant volume process, we have del E equal to Q plus W equal to Q minus P delta V equal to QE because P delta V is 0. Why 0? Because our constant volume process delta V is 0. For the constant pressure process, volume expansion work is given by minus P delta V. Therefore, if the system does the work, then delta E equal to Q minus W, delta E equal to Q minus negative P delta V, it becomes Q plus P delta V, which is QP or delta H. It means delta H equal to delta E plus P delta V for gaseous systems. I repeat, delta H equal to delta E plus P delta V for gaseous systems. It should be remembered that by convention W is always taken as minus delta, minus P delta V. Evidently, Cp is greater than Cv by the quantity P delta V. It can be shown that Cp equal to Cv plus R for 1 mole of substance and Cp equal to Cv plus Nr for n mole of substance, gas substance. And when I mean gas, I mean ideal gas. What is the proof? So PV equal to nRT, the famous gas equation for ideal gases. If we increase volume at constant pressure, it becomes P V plus delta V equal to nR. It means Cp is greater than Cv by amount P delta V. Second method. We know that enthalpy H is a state property. It is a homogeneous function of temperature and pressure. Also, H is defined at E plus PV. Taking differential, dH equal to dE plus PdV plus BdP plus dPdV. Here dPdV can be ignored because it is in finite assembly small term. At constant pressure, VdP can be ignored because it is 0. Therefore, dH upon dt at constant P equal to dE upon dt at constant P plus P dV upon dt at constant P. Very important equation, question number 4, remember it. Now, the term on the left hand side of the above equation is Cp. We need to evaluate the two unknown terms on the right hand side of the equation. That is dE upon dt at constant P and P dV upon dt at constant P. These terms are to be evaluated. How can we evaluate these terms? The principle is the variable E is again a state property and it is a homogeneous function of state variables, temperature and volume or temperature and pressure. So we begin with E equal to E is a function of T and B. The complete differential of E, that is dE, can be written as the sum of two partial differentials with respect to T and V. This is followed by differentiating the resulting equation with respect to T and B at constant pressure. So E is a function of T and V. It means d over dt at constant V dt plus d over dv at constant t dv. Differentiating with respect to temperature at constant pressure becomes d over dt at constant p equal to d over dt v into dt over dt p held plus d over dv at t constant dv over dt at p constant. The first term on the left hand side is Cv. So in this way we have evaluated d upon dt at constant p. It is equal to Cv plus d upon dv at constant t into dv upon dt at constant p. We will put this value, equation 5, into equation 4 and derive equation 6, which is Cp equal to Cv plus d over dvt into dv over dv dt p plus p dv over dt p, taking common, which is common, dv over dt at constant p is a common term, so we derive equation 7. Equation 7 is valid for real gases. For ideal gases, Joule's experiment shows that d over dv at constant t is 0. Further, differentiating the equation PV equal to nRT at constant p with respect to t, so that p dv over dt at constant p equal to nr. Therefore, equation 7 becomes equation 8. It is valid for n mole of ideal gas, and equation 9 is valid for 1 mole of ideal gas. Equation 8 is Cp equal to Cv plus P del V over del T at constant P equal to Cv plus Nr. Equation 9 is Cp equal to Cv plus R for 1 mole. For monoatomic gases, translational kinetic energy E is 3 by 2 kT. How? Differentiating it with respect to T at constant V gives d upon dt at V equal to R. That is Cv equal to 3R by 2. And therefore Cp equal to 3R by 2 plus 1 means 5R by 2. As compared to monatomic gases, it takes twice the heat to raise the temperature of polyatomic gases. Hence their Cv is 3R. And the ratio Cp by Cv is called gamma, a specific constant for each gas. In this way, we have covered first video. In brief, I must tell you, thermodynamics is very systematic study, very lengthy, very important. One must read it carefully. What is necessary? A little bit knowledge of differentiation and integration is essential. Those who are from biology background, not studying maths, they need not fear. Very simple equations, very simple rules are used. In the next video, at several places, I will give the formula also. So I repeat once more, differentiation and integration are not very difficult to understand. Preliminary ideas of differentiation and integration should be learned by heart. Otherwise, thermodynamics is very systematic. Though it is mathematical, my students need not fear it. The subject is very important, very important, very important, and very systematic. It can be easily grasped. So I finished with the first video, and I hope if you read this a few times, you will grasp the matter. Please like and subscribe to the channel. The channel name is chemistry_gist. Thank you very much.